Hey everyone! In this video I'd like to show you how to make a Fibonacci number generator in Logisim. First, if you're not familiar, Fibonacci numbers are part of a sequence in which every term is equal to the sum of the previous two terms, starting with the numbers 0 and 1. We add those together to get 1, then add 1 plus 1 to get 2. Then 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. I wrote a program in Python which generates Fibonacci numbers, and I know some of you might not be familiar with programming, but that's okay too. I really just wanted to have a series of steps that we can follow, and then we can think about how we might implement those in hardware. It's really quite a simple program, and I'll just walk you through it step by step. So first we have our function, Fibogen, which takes in a single number, n. Now the first thing we do in this function is we set three variables, a, b, and c, and we set them to the values 0, 1, and 1. Next we enter a loop which repeats n times. And the first thing we do in the loop is we print the value of a, which will first be 0. Then we update c to be equal to a plus b. Then we update a to be equal to b, and b to be equal to c, essentially pushing the values up through the variables a, b, and c. So first we'll print 0, then we'll take 0 plus 1 and put that into c, which will be 1. Then we say a equals b, which will be 1, b equals c, which is 1, and then we do it again. We print a, which is now 1. We then update c to be a plus b, which is now 2. And we push our variables up. So b equals c, or rather a equals b first, which is 1, and then b equals c, which is 2. And then we just do that again and again. So this will then be 3, and we update a, and we update b. And then this will be 5, we update a, and we update b. And on it goes. So let's just run this program to make sure that it actually works. Alright, we've got 0, 1, 1, 2, 3, 5, 8. Alright, looking good. I think it works. So how can we implement this in hardware? Well, since our program uses three variables, I'll be using three registers. Registers really are basically just variables. They store data. So let's label them, just like in our program, A, B, and C. Okay. First, we want to initialize our registers. So that's easy enough for register A. We will simply pulse its reset line. All right, I'll bring that out here, and we'll do stuff with that later. However, we're not going to actually do that for register C. Even though we do that in the program, the first thing that we do with C is actually set it to something, a plus b, which will be guaranteed to be initialized to known values. So all we have to do now is to set b to the number 1. And to do that, I'll be using a constant value. Basically, we're hardwiring the number 1 into the circuit. Now, we can't really plug in the number 1 into register B directly. And why that is because we will also be putting in C into B later, since we want to push the numbers up through the registers. And doing this would create a conflict on the input line for B. So instead of that, we'll be doing it a little more indirectly through something called controlled buffers. So normally if we attempted to drive conflicting signals onto a common line, we would get an error. However, with the controlled buffer, what it does is it actually decides whether to actually drive the signal onto its output line. So when its bottom input here is low, it is not allowing the signal through. But when it goes high, it does allow the signal through. And so that way, we can, in a sense, select among different inputs which ones we want to drive onto the output line. For B's input line, we're going to be using two buffers. One of them is going to be selecting the input number 1, and the other will be allowing the value of C to go through, like this. So that way, when we're setting up our circuit, we control this buffer so that it can allow the number 1 to go into B, but during the main loop of the circuit, we actually enable this buffer to allow the value of C to go into B. How we're going to be controlling these buffers is through a memory circuit called the SR flip-flop, sometimes also called the SR latch. And how it works, I'll set it up real quick with a couple of buttons here, is that you can pulse, when you pulse this line, it will remember to output the number 1, even when the original input has returned to 0. And if you pulse this line, it will remember to output the 0, even if the original input has returned to 0. So it simply set and reset. You can set it to 1, you can set it to 0. Now, since what we want to do when the circuit first starts up is initialize B to the number 1, we're going to be using the sort of inverse of the SR latch's output. And we'll feed that into this buffer's control input. So by default, when the circuit turns on, we will be driving the number 1 onto this line. And later, we will set the SR latch so that we can drive the output from C onto B's input line. Alright, let's take a look at our program again. Now, in the main loop, we are updating C with the value of A plus B. Therefore, I'll be placing an adder circuit. All it does, really very simply, is it takes in 2 inputs and it outputs the sum. We'll feed that directly into C. Now, registers do not update constantly with the value that is on their data input line. I'll show you what I mean. So here I'm inputting, some 32-bit data into my register, but you notice that it's not actually updating with the value. Registers normally will only update with the value that's being driven onto their input line when their clock input is risen from 0 to 1, like this. So what I'll be doing is I'll have a line to all the different clock inputs for the different registers. I'll take them all the way out to the left side here. And then I will arrange them like this. So what I'll be doing now is I'll be placing pull resistors on each of these clock inputs. And why that is because we kind of aren't really driving a signal onto these lines. And the way that the clock inputs work is they really only update the register when the signal rises from 0 to 1. However, if we aren't sort of setting a default value for them with pull resistors, we would be raising them from undefined to 1, and that is not guaranteed to work. And before I forget, let me bring out the inputs for our SR latch as well. So why I bring out my circuit's control inputs like this is really just for organization. I've always found that having them out here like this lined up grants me easier access to control everything. Alright, I forgot one last thing to do over here. I need to make sure that register A can be updated with the value of register B. So let's bring a line over here to register A. Alright, I think now our circuit is ready to be controlled. But how exactly can we do that? Well, let's try doing it manually first. I'll set up some buttons over here, and then we can manually control all of these lines. The first thing we want to do when our circuit turns on is make sure that this SR latch is in its default state. So let's find that line, and we will pulse it by pressing this button. Okay. Next, let's look at our program and see if we want to reset A and set B to 0 and 1. So we reset A by pulsing this line, alright, and we will set B by pulsing its clock input. And note that, of course, the value being driven onto B's input line is the number 1. So we pulse this line, and B has now been updated with the number 1. Now, we're going to skip this step because we actually don't need to do that. since the very next thing we'll be doing with C is updating it to A plus B. So now, let's pulse this line. Alright, and notice that control on B's input has been switched to select C's output. Now, we're going to update C with A plus B. So we find C's clock input, and we have that. Next, we want to move B into A equals B, so we pulse A's clock update, and we pulse, B equals C. So we find B's input, and we pulse that. Okay, and then we just do it over and over again. So let's see, C, and then A and B, C, A, B. So it's these three. So we're just going to do C, A, B, C, A, B, C, A, B over and over again. And as you'll see, we are generating Fibonacci numbers this way. Except that's very confusing, isn't it? If you're not familiar with hexadecimal numbers, this is how to write 13 in hexadecimal. So, to make things easier for us humans, let's add a probe. It will allow us to see what the value is written in normal decimal numbers. So now we can semi-automatically generate Fibonacci numbers. But wouldn't it be really nice if there was just a circuit that could do all this stuff for us automatically? Well, lucky there is. Let's get rid of all this junk. We will not be needing it. To automatically control these lines, I'm going to be using something called a demultiplexer. Let me just show you real quickly what it does. I'll set one up. How a demultiplexer works is it takes in an input, and it allows you to select from one of n outputs to drive it on. So right now we're outputting on the first output, but if I change the control input on the demultiplexer, we can change where the output goes to. So we can drive it on the first output, we can do the second, the third, or the fourth by just changing the demultiplexer's control input, or what's it called? Select. That's what it's called. I have replaced the input pins on the demultiplexer's select input with a device called a counter, which simply counts by 1 every time its clock input has been risen from 0 to 1. This is going to be kind of the basic functionality behind the control circuit. So let me just set up a few more things. I'll get rid of this, and I'll move this back a little bit. In fact, we're going to use something called the clock. It's really self-explanatory. It's a clock. It ticks on and off at a regular interval. So what I'm going to do now is add something called the inverter, or the NOT gate. And all it does simply is it takes in whatever input it's receiving, and it outputs the opposite. Where I'm going to use this is, let me move back here, on the counter on our demultiplexer. And why that is we want the clocks, or we want the counter to update to the next output line when the clock output is low. Otherwise, it will send a signal and count up at the same time. And we don't want that. We want it to send a signal, then to count. So it'll go like this. Another thing we want to do is add a sort of a gate on our clock signal to decide whether it actually goes through to our demultiplexer or not. And why we do that will become apparent pretty soon, but basically we're going to need 2 of these, and we want only one of them to be active at a time. And now how we're going to do this is we're going to use an SR latch and an AND gate. Let me get it to the right size. Okay, and all the AND gate does really, it takes in 2 inputs, and it basically just says if both of the inputs are on, then the output shall be on. Otherwise, the output shall be off. Or basically it says if this input and this input are both on, then the output is on. Okay, so we're going to plug in the SR latch there, and the clock signal here. Let's drag that out here for now. Okay, so now when this SR latch is set to on, the clock signal will actually go through to the demultiplexer. And when it turns off, well, it won't. So now we're going to want to use some controlled buffers. These will allow us to drive the clock signals onto the control lines for our main circuit. And why we're using controlled buffers instead of driving these lines directly is because that might create a conflict on these lines when we add more things later. So let's find out which lines do we need. We know that when our circuit turns on, we want to set register A to 0 by pulsing its reset input. So that's the first line. And that we also want to make sure that this SR latch is 0. And that's the second to last line. So I'll put 2 controlled buffers for now. Okay, let's take a look at our program again. We want to then load in 1 into B. So that will be simply pulse its clock update input, and that is the third line. So I'll put another buffer here, and then finally, to get things ready to enter our loop, we will enable this SR latch. We'll set it to 1, and that is done by pulsing the last line. Alright, so now let's connect our buffers onto these lines. We need the first and the second to last. Alright, plug that into there. Alright, and then we needed the third line. 1, 2, 3. And then the last line, right? There we go. Now we're going to plug in the buffers into the demultiplexer. Okay, so the next thing we want is when we've sent out the last signal to enable the SR latch. All right, let's make sure that's right. Yep. We want to disable control on this part of the control circuit by disabling the SR latch up here. Now how we're going to do that is using something called a falling edge detector. It's very simple. All it does is when it detects that a line has gone from high to low, it will send out a very brief signal. Alright, so how I build the falling edge detector is simply with an AND gate and 2 NOT gates. Now to demonstrate how it works, I'll just quickly add on an input and an output. And then I will run the simulation step by step so you can see how the signals propagate. So first let's bring the input signal to high. Alright, so the falling edge detector, when this signal goes low, like this, what's going to happen is it goes through this inverter and it will input 1 on this input, and it will input 0 on this input. However, signals do not propagate instantly. So there will be sort of a lag as it goes through this inverter, during which the inputs on the AND gate will both be high for just one moment. Watch. So now let's get rid of this, and we'll get rid of that. Bring you over here. And now what we want to do is when the third clock cycle is done, when it returns back to low, we're going to disable this SR latch. So let's take a quick look at how this is going to work. Okay. We'll pretend that we have some button somewhere that enables this SR latch, and then we press it and it goes 1, 2, 3, and it doesn't reach the fourth output. It turns off when it gets to the end of 3. Okay, so let's take a look at our program again. At this point, everything should be set up. We want to now enter the main loop of the program. So we aren't going to really need any special circuitry for this, since we already have our probe set up to read directly from register A. Let's see. So now we need to pulse the line to set C to be A plus B. And then we pulse a line to shift B into A and C into B. Alright, so let's figure out what those lines are. We need to first pulse this one. So that's the third from the last. And then we can pulse this one and this one. So second and third. Fourth, second, and third. Okay. So we're going to place one buffer for updating register C and two more for shifting the registers C into B and B into A. So let me just plug these in real quick. Alright, now let's build another one of these demultiplexer control circuits. Alright, so we've got this one set up now. You might notice that this demultiplexer only has two outputs, even though we're going to be driving three different lines. And why we do that is actually because we don't have to drive these two lines on separate clock cycles, as in we can actually shift C into B and B into A at the same time. So these two we can actually do at the same time on the same single clock cycle, which means that this part of the circuit, or this program, really only needs to have, in a sense, two instructions, two separate clock cycles for it. Okay, so let's find out which lines do we need again. First we want to update C, so we need the third from last line. So I'll plug that into third from last, 1, 2, 3. Alright, then we will need the third and the second, right? Okay. The third and the second. There we go. These two will be on the same clock cycle. And now let's bring this over a little bit closer. Connect them like that. Alright, now we just need to connect this into our clock device. What's going to enable this control circuit is going to be the signal from the falling edge detector on the first part of the control circuit, the part that essentially says when this part is done. So we bring this down and enable that. So now we're going to add our power button, which can also serve as a reset button. I'll put that right here, and all it's going to do is, let's see, we want to have it enable this. Alright, so I'll bring that over there. We want to make sure that this is set to 0. Alright, well, maybe I can make it look neater that way. Okay. And we want to make sure that this is turned off, and this is also set to 0. Everything else, part of resetting or initializing, will be handled by the control circuits. Alright, let's give it a quick test run, shall we? Let's bring our probe over here and bring our Fibonacci numbers over here so we know what we're looking for. Alright, we can move that closer. Why not? Okay, and now let's turn it on and see what happens. Alright, there we go. Looks like it's working. It's making Fibonacci numbers, people. It's a machine which prints Fibonacci numbers. Okay, so I hope you enjoyed that. If you like what you saw, feel free to share it with your friends. If you want to see more, don't forget to hit the subscribe button and click the little bell icon. With that, I'll see you in the next one.